All right, so here we are, ICP. We're taking a look at the Calorimetry Lab, or specific heat lab. And you saw on Google Earth the instructions, and you've been hopefully getting some of that done. What we're going to do right now is take a look at the calculations and help you out. So please realize that first you want to do is take the numbers that you got on your lab and figure out which ones go where. So we'll take a look here at this. So if we think about the copper, a beginning, and if you remember we had a piece of copper here, it was actually cylindrical, wasn't it? So it didn't have this shape when we went to our actual lab. Okay, it was a piece of copper and you weighed it, and the student got 124 grams when they weighed it, so that the mass here would be 0.124 kilograms for their copper. They also got the weight of the water ahead of time. And let's see if they have that piece of data here. I guess that's what that one is there, so we'll go with that. So 0.198 kilograms for the mass of the water. And the water was initially colder, 22.4. And so we'll go ahead and record that 22.4 degrees Celsius. When the hot metal got placed into the water, it warmed up, and we can see at the end the temperature was 24.3 degrees centigrade. Notice that the copper metal that we had was actually in a hot water bath that's not being shown here. We really don't care about that hot water bath. The whole point of the hot water bath was simply to get this piece of copper hot enough that we could change the temperature by placing it into the cold water. So when we see here where the student wrote hot water is 60.9 degrees, it's not important that the water was that temperature. It was the only way we could measure the temperature is to have it in the water. What matters is that that 60.9 degrees, okay, is actually the temperature of the hot metal as we took it out of the hot water and placed it into the water. So I saw in some of the labs, some people were recording the hot water temperature before and after you put the metal into the hot water. And that doesn't really matter. All we want is the temperature of the hot water as we took the metal out of it right at the end in order to use it to place it into the cold water. So don't confuse the hot water bath. We don't really need it. All we need is the temperature from it so that we know the temperature right here of the hot metal that we're going to place into the cold water. It sits there for a while. The water warms up. Now that we have the metal inside the water, okay, and we have this new temperature of 24.3 degrees. Okay, and that's the basics of the lab. So now what I'm going to go ahead and do is look at the calculations that we do, for example, on this case. And so let's take a look. We're going to use Q equals MC delta T. And so I'm going to say the Q equals MC delta T, as we talked about in class, for the water actually changing temperature. So what we're going to do here is for the mass, we're going to put in the mass of the water, which is 0.198, and that's kilograms. We're going to multiply that by the C of water, which is 4,184. We're using, sometimes you'll see 4.184, but we are using 4,184. And that's because the unit we're using for mass is kilograms here. Okay? And the units on this C value are a bit complicated. We have joules per kilogram per degree centigrade. Okay, now we need the delta T. In order to get the delta T, what you're going to do is you're going to take your calculator and you're going to look at the temperature at the end, which was 24.3 in this case. And you're simply going to subtract the temperature at the beginning, which was 22.4. That gives us a temperature change of 1.9 degrees centigrade. Okay, and from that we're going to be able to get the energy that actually went into the water. So we go 0.198 times the 4,184 times, and I'm just going to grab the answer from before, the 1.9. Do that again. So we have the 0.198 times 4184 times 1.9. And so we get about 1574 joules. Okay, so this is the energy in joules that the cold water received as it warmed up and became the hot water. That means that whatever metal it was, had to lose that amount of energy. So now we're going to do the Q equals mc delta T for the piece of metal. And the piece of metal, the Q, we know has to be the same amount of energy that was gained by the water, must be the same amount of energy that was lost by the brass. So we're going to be able to use this 1574 joules and set it equal to mc delta T of the metal. So now the M of the metal we had here of 0.124 kilograms. Okay, now this metal is not water, so we're not going to use the 4,184. In fact, the point of the lab is the specific heat of a metal, and that's what we're trying to find. Some of you like to put an X here. I'm just going to put a C. If it makes you feel better to put an X there, so you use all your math skills from your other math classes, feel free to do so. And now we need the temperature change that the metal went through, which is a lot more. So we're going to take the 60.9 and we're going to subtract from the final temperature here, which is 24.3. Okay, so we have a 36.6 temperature change. Okay, and now what we're going to do is solve for C. So I'm going to first just multiply these two numbers. So I'll take that times 0.124. So now I've got a 4.5. So I've got 4.5. I'll go ahead and round that to 4. C equals 1574. So on the calculator, I can take the 1574 divided by the answer. It'll grab all the sig figs there when I do it that way. And I get a 347 essentially. Okay, so I'm going to call that C equals 347. Okay, and again, this is joules per kilogram degrees centigrade. Now, if we look at the expected values for copper, if we take a look here, pull this up so you can see it, you can see that copper had an expected value of 385. Notice this is in grams, not kilograms, so we need to move the decimal over to compensate for the energy amount that's needed. So this would be 385. So the expected value, C expected, is 385. Okay, and these numbers are not the same, and we're not surprised by that really. You know, it's not a perfect lab. We know that when we were moving the heat, the big piece of hot metal over into the water, we lost some temperature along the way. We know our thermometers are not perfectly accurate. We're not surprised to see a little bit of a difference. So that's why we did multiple trials. So you're going to do this exact same calculation for trial number 2 and then trial number 3, and you'll calculate a C value. It's doubtful that you'll get 347 each time, but you'll get a different number. Get those 3 numbers for C, and then average them. Okay, so I'm not going to go ahead and do that. You just do this exact thing. You can just rewind the video and watch again if you need the help with that. So I'm going to pretend that I only had time to do one trial, so instead of using the average, I'm going to go ahead and use the 347 in order to get my percent error. Okay, so I go percent error is a comparison between what I got, my value, which is going to be 347, minus the expected value, which is 385, divided by the 385, the expected value. We're going to times 100 because we want a percent. And so we can take a look here. We're going to use parentheses and go 347 minus 385. And we're going to divide by the 385. Okay, we move the decimal for percentage, and we get about let's call it 3.9%. Okay, so we get a negative we get a negative 9 point, I think I misspoke there. We get a negative 9.9%. Okay, the negative just signifies that our answer was smaller than the expected answer, which is nice. And we have a 9.9%, which is about right for this lab, not a bad result at all. Okay, and that's how you do the calculations for the calorimetry lab, where we're calculating the specific heat of a metal. I hope that helped. You can come and see us, any of the teachers, at lunch if you need more help. Good luck. Thanks.